Welcome to lesson 7 of the Force and Space scheme. This one is on Galileo's experiment. Now, for those of you who don't know what this lesson title is referring to, you probably heard of the experiment, maybe not referenced to Galileo, but it's this idea that if you drop two objects, one heavier than the other, what we intuitively expect, and I think most human beings intuitively expect this, would be that the heavier object, because we kind of visualize it as having a kind of greater force, because it's got that greater force, it should accelerate faster, and then when you drop them together, it should fall to the ground first. Now, Galileo, supposedly, I think it's an apocryphal story, but supposedly went up to the Tower of Pisa and dropped a cannonball and some other object that I can't remember, from the top of the Leaning Tower of Pisa, where he was a professor at the University of Pisa, in order to investigate this once and for all. Now, whether he did that or not, he was the person who gave us this new way of thinking about why they fall or accelerate at the same rate, which is to do with this idea of inertia. So really, this lesson is all about inertia, and when I say that, really what that means is it's just another application of that core idea we introduced in the first lesson in this sequence, number 4 of this scheme, what is a force? This idea that if there's a force acting on the object, it changes its motion. What we're doing now is just refining that a little bit, essentially so we take into account the mass. So how I would do this, I mean, I'm sure you will find videos on the internet if you want to do a kind of introductory thing, because it's quite a nice thing to show to students. But what we want to draw in order to make this really explicit to students is the two ways of thinking about this, because we want to really unpick their prior conception, and probably they're still dealing this. A lot of them will still be working under this kind of Aristotelian framework, and we want to show them why that's wrong and why the Galilean Newtonian framework gives a more plausible explanation. So what I'm going to do again, I've done this a few times so far in this scheme. I'm going to compare Aristotle, his view of the world. They're really going to hate this guy Aristotle by now, because he's taught them all of these terrible things that are wrong. But hopefully they can see it in a bit of context. I'm going to compare that with the Galilean Newtonian view. Hopefully they will see that this one is a better way of thinking about it. So what I'm going to do under the Aristotelian view is draw two objects. So let's draw, we'll do a football and a bowling ball, because they're the two objects that I've used in the independent task. And what I'm going to do is say this football has a mass of 0.5 kilograms, and this bowling ball has a mass of 5 kilograms. You might want to put 5.0. Because you want them to see that this is 10 times greater than this one. Now, the Aristotelian way of thinking about this would be as follows. So if we draw the forces acting here, I can squeeze my ruler in there. What the Aristotelian view says is, okay, that's got a force like that, and we can show that different size forces have different length arrows. So then I'm going to draw a much smaller arrow on here, like this. It doesn't need to be to scale at this point. Hopefully that illustrates the point that this is going to have a much bigger force than this, which is correct so far. I've just realised I've got these the wrong way around. Apologies. So it should of course be the other way around. So this has a much smaller force than this one. Now this is, so far, this is correct, and this builds upon the knowledge that we saw last time. But where Aristotle went wrong is he said, well, look, because this has a much bigger force, let's say a 10 times bigger force than this one, that means this acceleration, and this is where I'm going to introduce this idea of acceleration, how much an object speeds up. This is going to start moving and start speeding up much more slowly than this one. Now actually, so I'll show the acceleration here, like this. Now actually, this is a bit of an inaccurate picture. What Aristotle actually thought was that objects just hit they have a kind of fixed speed and they just hit that immediately. So they go immediately from not moving to moving at a constant speed. He didn't really think about it in terms of acceleration, but we can kind of gloss over that. But the point is, it's that link between, okay, this one's got a smaller force, so it's going to have a smaller acceleration or a smaller constant speed. This one's got a bigger force, so it's going to have a bigger acceleration or constant speed. So what you would see then is that when these two objects get down to the ground, which I'll draw down at the bottom here, what you would see, if that was true, is that this one hits the ground first, this one should still be up in the air. That's what they would expect to happen. But what Galileo's way of thinking about this did was give an alternative explanation of what's going on. So let's draw our two objects again. Our football and our bowling ball. So this is 0.5 kilograms. This bowling ball has a mass of 5.0 kilograms. Now, again, we can build on the knowledge from last time and say, well, okay, I know that the mass here, the difference in mass, or one mass is 10 times greater than the other. So, in this case, my gravitational force here, because the gravitational field strength is the same for both objects, this is going to have a smaller gravitational force, this is going to have a much bigger one. And actually, the difference between those is 10 times. Because this is 10 times greater than this, well, this force is going to be 10 times greater than that force. But here's where Galileo came up with a really new idea, and Newton then turned this into his, well, kind of his first two laws of motion, which is, if this has a 10 times greater mass, then it must also have 10 times greater inertia. So what we can add here is a new word, which is inertia. And essentially that means how much force is required to get an object moving. How much force is required to cause it to accelerate at a certain rate. Now Galileo's argument was as follows, and this is where we're going to see the really clear difference between the Aristotelian and intuitive picture and the modern physical picture. Galileo argued, he said, well, look, if this has a 10 times smaller mass, then it only needs a 10 times smaller force to get it moving. So this is going to accelerate, let's say, at that. Now let's look at this one. This has a 10 times greater mass, so in order to get it accelerating at the same rate as this one, well, it's going to need a force that's also 10 times greater. But look, that's kind of baked in to what we've worked out already to do the gravitational field strength. We said, well, the mass is 10 times greater, therefore the force is 10 times greater. So effectively what's going on here, I mean, we may not want to bring in the algebra now, but effectively what we're looking at here is this idea of A equals F over M. That's the idea of inertia. But you can just say, look, this is 10 times heavier, so it needs this 10 times bigger force just to get it accelerating at the same rate. And hopefully what you can see here is this really clear difference between this account, which doesn't have this idea of inertia baked into it, and this account, which does. And this is the key difference, and this is, you know, a really important concept that students won't have thought about. It's not a very intuitive way of thinking about it. If you've got a 10 times greater mass, you need a 10 times greater force to get the same acceleration. So in that case, if they're both accelerating at the same rate, well, what would you expect to happen? Well, you'd expect them to accelerate at the same rate, and they both hit the ground at the same time. And you can see down there. Now, obviously, this doesn't always work perfectly. The account I've sketched so far ignores air resistance, and you can talk about that. And again, this comes back to this idea that Galileo and Newton, building upon that, they were able to imagine this idea of a vacuum. Let's imagine we had perfectly empty space without any particles, any air resistance, any friction, drag, whatever. This is just one of the reasons they were such profound thinkers, is that they could think of something that they didn't even know existed, but they could imagine and use that imagination to really develop some novel ways of thinking about the world. And you can, obviously, I'm sure you've seen this already, you can find a video of Brian Cox doing this same experiment with, instead of a football and a bowling ball, he does it with a feather. It's a bowling ball or something super heavy, but he does it in a vacuum. And even then, in the vacuum, even with two wildly different objects with different air resistance as well, in the vacuum, they fall at the same rate. And that's, it's a great one to show to students, and it's a great one to get them thinking about this concept, which is inertia. We're going to move on to more drawing lots and lots of force diagrams in the next lesson when we look at balanced forces, and then after that unbalanced forces. So I will see you there.